continues. As that continues, the pressure builds, because the white dwarf is basically solid matter, and you have gas falling on it. At the base of the gas, the pressure is growing, and the temperature is growing. Well, this is an unstable situation, because eventually there's enough gas pressure down on that hydrogen layer that it ignites. Spontaneous thermonuclear fusion. Well, the sun is doing that in its core every second of every day.
So why can the same kind of nuclear fire that quietly powers our sun turn a dead star into a cosmic explosion? At the core of our sun, hydrogen nuclei are constantly merging into helium in a process called thermonuclear fusion. Thermo means it's driven by very high temperature, and fusion means lighter atomic nuclei combine into heavier ones, releasing energy. Every second, the sun converts hundreds of millions of tons of hydrogen into energy, yet it doesn't blow itself apart. The reason is balance. Gravity pulls inward, trying to crush the star, while the hot, high-pressure gas and light from fusion push outward. This balance, called hydrostatic equilibrium, acts like a natural regulator, and it's the baseline we need to understand before we ask how things go catastrophically wrong. A star that has become a white dwarf is what happens when that regulator loses most of its control. A white dwarf is the dense core left behind when a sun-like star runs out of fuel in its center and sheds its outer layers. It packs roughly the mass of the sun into a sphere about the size of Earth. That means a teaspoon of white dwarf material would weigh several tons, thousands of kilograms. This follows from simple density, since you're compressing roughly a solar mass into a planetary volume. What holds it up is not hot gas pressure anymore, but something called electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed into the same quantum states. Crucially, this pressure does not depend strongly on temperature, unlike normal gas pressure. That single detail quietly removes the thermostat that keeps an ordinary star stable. How does that missing thermostat turn gentle fusion into a runaway blast? Imagine a white dwarf in a binary system orbiting close to a normal star. Gravity from the white dwarf can pull gas, mostly hydrogen, from its companion, letting it accumulate in a thin layer on its surface. As more gas piles on, the layer at the bottom gets compressed by the weight above it, becoming hotter and denser. In a normal star, as fusion turns on and heats the gas, the star expands, which cools the gas and slows the reaction, a negative feedback loop. But on a white dwarf, the underlying support comes from electron degeneracy, which hardly changes with temperature, so the layer cannot easily expand to relieve the pressure. Once the base of that layer gets hot enough for hydrogen fusion to ignite, the temperature rise makes the fusion rate skyrocket faster than the material can adjust. That is a runaway thermonuclear reaction, and it powers what we observe as a nova. A quiet but important fact here is that the difference between a stable star and a stellar bomb is just whether that feedback loop is negative or positive. In the sun, more fusion means more heat, which means expansion, which then cools the core and reduces fusion, a self-regulating cycle. You can think of it in everyday terms. Heating the air in a balloon makes it expand and become less dense, which limits how much further it can be compressed. In degenerate matter on a white dwarf, it is more like a nearly rigid metal sphere. Heating it barely changes its volume, so the pressure and density can keep rising. The hydrogen layer on top behaves more like the fuse on that rigid sphere than like the flexible gas inside a balloon. When fusion turns on in that confined layer, the energy has nowhere to go at first except into further heating, which accelerates the reaction instead of calming it, so the overlying gas is blasted off in a sudden flash. The white dwarf survives, but the nuclear fire has briefly behaved more like an explosion than like a star. What happens if the white dwarf keeps gaining mass and the instability reaches not just the surface, but the whole star? There is a theoretical maximum mass for a white dwarf, called the Chandrasekhar limit, of about 1.4 times the mass of the Sun. It appears when you apply quantum mechanics and special relativity to electron degeneracy pressure. Above this mass, degeneracy alone cannot support the star against gravity. If accretion pushes the white dwarf close to this limit, its interior, made mainly of carbon and oxygen, can reach conditions where those heavier nuclei start fusing. Because the entire star is supported by degeneracy, that ignition also lacks a good pressure-temperature regulator. In one leading scenario, consistent with many observations, though not the only path nature may use, the outcome is a type Ia supernova. The whole white dwarf is destroyed in a single, global thermonuclear runaway. The surprising twist is that even though these explosions are not perfectly uniform and their peak brightness can vary, their light curves follow patterns that let astronomers standardize them into practical distance markers, often called standard candles, which helped us map cosmic distances and discover that the expansion of the universe is accelerating. The calm glow of our sun and the violent death of a white dwarf are two outcomes of the same underlying rule. Gravity and pressure either find a stable truce or they don't. In the sun, hydrostatic equilibrium and temperature-sensitive gas pressure keep fusion in a controlled, steady state that can last billions of years. In a white dwarf, quantum mechanical pressure takes over, largely disconnecting pressure from temperature and removing that control mechanism. Add fresh fuel on top, or push the whole star close to its maximum mass, and the same fusion process becomes unstable, racing away faster than structure can respond. So, the reason a white dwarf can erupt while our sun shines steadily is not that their nuclear physics is different, but that their thermostats are. One has an effective feedback loop, and the other has almost none. And that points to a broader lesson. Many systems in the universe, from stars to climates to even human technologies, can flip from gentle to catastrophic when a feedback sign changes or a critical threshold is crossed. Like, if this was interesting, hit the subscribe for more and turn that notification bell on.